Han Liu asked me if I could suggest someone to talk about the eclipse coming up in 2017, and I thought hard about this for about a week, and he came back and said, have you thought of anybody else, anybody at all? I said, well, yeah, most of them are in Hawaii, and the other ones, I don't know what they're doing, and so in the end, I rather unashamedly volunteered to talk myself, so I apologize for doing that. My perspective today will be from a physics point of view. I don't believe you can talk about physics in too elementary a way. That's why I went into physics in the first place, and why I didn't go into something like system science, which I find to be very, very difficult and tricky to understand. And I'll start out by saying that I think that sometimes we get a bit lost in our endeavors at a national center by getting involved with more of technology than the actual questions that we ask. So I'm going to ask some basic questions today. And to start that off, I'm going to include a very famous figure from a monograph by Keith Moffat in 1978, which I'll explain later. But it basically shows you something called magnetic helicity. Basically, in a divergence-free vector field, has a constant of the motion associated with it. If it's in, for instance, the example of magnetohydrodynamics, if it's an ideal MHD, the flux tubes are frozen, you can't break field lines, and as the system evolves, it must continue to obey a conservation law, namely the conservation of helicity. And as one gets to very close to ideal conditions, it still approximately holds that the helicity defined in a very careful way is a constant of the motion. And I'm going to talk about how the infrared measurements we can make might address the evolution of the solar cycle from the point of view of not only the evolving magnetic field, but its intrinsic magnetic helicity. Yeah. So first of all, I'll talk about the scientific motivations and questions. Then I'll compare what we can learn from infrared and visible regions. And then I will introduce the eclipse of 2017, August 21, and I'll talk a little about the future, which is what this really is all about. I want to start with an annual review paper by Mei Zhang and Boon Chai Lom. Mei was a visitor here for a couple of years and has been a continuing visitor here with various of the staff. And they wrote this very nice review in 2006. I'm going to draw upon that. And they say a very interesting few sentences, which I will read out because I think they're very profound if true. We view coronal mass ejections as the final stop in the sun of a process of magnetic helicity transport. Magnetic helicity created by solar dynamo in the interior is transported into the corona and accumulated in magnetically closed coronal regions. It is finally ejected to infinity when the confinement fades. This is a repeated and never-ending process driven by the field seeking the minimum energy state. So I think you can see in a review have a rather elementary, but that doesn't mean simple, but an elementary picture of what the evolution of the sun's magnetic field is about. It's not only about the fact that you have to reverse the flux every 11 years, but it's about something that's very close to a constant motion. And what they're talking about is that the sun generates internal helicity. Parker proposed this in 1955, and there's been many papers written on this subject since. But basically, the magnetic activity is an intrinsic thing, magnetic helicity is an intrinsic thing generated by any dynamo, and this thing has to be conserved, and yet we see the entire flux of the magnetic field change every 11 years. So this helicity has to go somewhere. Here is, just to clarify, a nice pretty picture, again from their review, showing what a CME is. It's an ejection of material from the surface of the sun. Their contention is that this has something to do with the solar dynamo. When you think about that, that's like saying the tail wags the dog. But as eloquently expressed by Axel Brandenburg about 10 years ago, boundary conditions on the dynamo are very, very important. Here is an example of the kind of data that are so, I think, as yet to be explained, but an intrinsic part of the solar cycle. Solar Maximum mission was launched in about 1980, and they started taking data. It then broke, and they sent a heroic astronaut up to fix it, and when it fixed, it's starting taking data again. And those kind of images I showed you, this shows you as a function of the evolving solar cycle, so solar maximum sometime in this period, solar maximum sometime in here. But this shows you the CME positions as a function of time in latitude. And you can see that the distribution with sunspots is extremely different. And the argument is by Yang Mei and these are important, therefore, for understanding, if you believe this conservation of helicity problem exists, that one must, therefore, look very carefully at the corona itself to see how the sun's magnetic engine is working. I just want to remind you that the top plot shows sunspots, and that's showing us essentially, as we believe, very strong fields generated by shearing layers somewhere in the solar interior, emerging at the surface. And these are of a toroidal nature. They go around the axis of the rotating sun, and the loops emerge preferentially at certain longitudes very often. The bottom plot shows you a manifestation of integrated magnetic flux systems. Very often you think these would also be toroidal structures, but those are very different. And so here we have two different origins of CME, most likely. One near the poles, one near sunspots. Okay, that's the phenomenology. So just to give you an idea of what the helicity is, of course, one can define it all mathematically very nicely. And the most illuminating paper I found on that actually is the one by Berger and Field, 1984. But from Moffat's picture, basically it measures the amount of, there's two kinds of helicity. One is an external helicity to a flux tube. So again, because there are no magnetic poles, the magnetic field lines of force don't end. If they're not ergodic, if they don't fill the space, then they have to occupy a region looking like a tube. And here we have two interlinking flux tubes. And by simple application of Stokes' theorem, you can show that this integral here, where A is the curl A equals B is the vector potential, that subject to a gauge choice, you end up with, actually not in this case because the surfaces are well defined of the magnetic field. So you end up with a measure of this thing called helicity, which is an integral over volume of something which has units of B squared L to the 4, and which measures actually the amount of interconnectedness of the magnetic field, or the twistedness. And the twistedness can be seen, first of all, let's look at the left one, where we have a picture showing the interlinking of two loops. If these are interlinked, not interlinked at all, then the helicity is defined to be 0, and you can show that from that integral there. If they're interlinked like this, and you just apply Stokes' theorem, you find it's twice the product of the two fluxes in those systems. That means that the flux is B times L squared, so it's got the right units of B squared L to the 4. If you go right, here we have an interlocked knot in the same way, only more complicated, a trefoil. Now, if you imagine taking a slice and, quote, reconnecting, just taking those things that are at the ends of that dotted line and sticking them together, I think you can see, and I always have trouble visualizing these things, which is why I would never do very well on those school tests at school where you have to connect things together and put blocks in and that kind of thing. I would always get very confused and essentially come to the bottom of the class. Probably still do, actually. But anyway, if you go from A to B and connect them up, then you'll see that that thing had some helicity beforehand because it's all interlinked. But if you look at it now, when it looks like that, you can see it's kind of got a twist to it. If you try to force it, it would be like forcing a hose pipe with some twist to it. And if it's sufficient, it would also writhe around the axis of the fields as well. And what you've done by reconnecting those is converting external helicity into internal helicity. So you can talk about a body of magnetic field having internal helicity. It's basically the amount of twist inside it. Okay. Everybody is very familiar with this picture, but I want to show something that is an example to make you, anybody that's never ever seen a picture of the corona in a twisted. This is a prominence, the first one detected famously in 1946. And I think you'd be crazy not to suggest that there is at least some twist associated with something there. Here we're looking at intensity of H alpha, which has nothing to do with the magnetic field, except that when the magnetic field, when the plasma is partially ionized at the least, the magnetic field is glued to the plasma. It has to move along the tubes. It can't go outside of it. And they seem to trace out magnetic tubes that are twisted. OK, what's this got to do with dynamos and stuff? Well, first of all, let's look at helicity. It's a measure of topology. It's an invariant in ideal MHD. It's equivalent to Alfvén's theorem, that statement, namely that once you put some plasma onto a flux, tube of flux, it forever belongs to that tube of flux, unless you snap it. And the conservation of helicity is saying essentially the same thing as that. If you don't have a change in any topology of the magnetic field, there's clearly no dynamo. I mean, you're not just getting magnetic flux, but you're actually changing the topology of the field as well. You have to do this. Observations and some calculations reveal essentially the same sign of helicity in each hemisphere, irrespective of the time during the solar cycle, whether it's North Pole or South Pole. This means that in each hemisphere, the helicity is forever collecting up, whatever that helicity looks like, however it's distributed with the sun. Now, there's a conjecture by Taylor and some work by Berger in 1984 that showed that the dissipation of helicity with time is essentially on the diffusive timescales of the size of the whole thing. This means that for any timescale less than about 10 to the 8 years, its helicity is essentially a conserved quantity. So it's almost invariant. And if you look at a class of models called mean field dynamos, you separate out your small scales from your large scales. The dynamo I'm interested in talking about is the large scale dynamo. We know we have interior convection and rather small scale regions where you have shearing motions. And the whole dynamo business is to try and connect the motions, the shearing plus the stretching and the twisting to produce a large scale dynamo. So one's looking at an inverse cascade process where you take very small scales and convert them to very large scale magnetic fields. That's one of the pictures that we have of the solar interior dynamo. Now, and to say it bluntly, the mean field dynamos work in an inverse cascade such that the mean fields, the very large scale fields, grow at the expense of the very small scale ones. The helicity does. But the helicity is conserved. So if you're ever building up helicity in the small scales at the same time. So we have to get rid of the accumulated H. In fact, Axel pointed in 2004 that this is part of a very serious problem, namely that, I take a quote from his paper there, is this secondary small-scale magnetic helicity that suppresses the mean field dynamo in a potentially catastrophic fashion. So it's like putting the pressure on a pressure cooker. Unless you let the stuff out, it's going to build up. And then from this mean field dynamo points of view, this small-scale helicity is going to destroy the ability for the dynamo to work. And he demonstrates this with some calculations in very elegant. So we have a couple of problems here. We've got to get rid of the H, and we've got to get rid of this problem of suppressing, in this context, the small-scale helicity as well, getting rid of that. So how does this all work? Well, the purpose of my talk is propose methods to study the role of proposed flow of helicity out of the sun using a technique, anticipating DKIST and maybe even Cro-Mag, Cosmo, and other instruments. So DKIST is the 2019 scheduled 4-meter telescope on Haleakala, and Cro-Mag and Cosmo are two HAO-led efforts to measure the chromospheric and coronal magnetic fields of the sun, respectively. The state of the art of this is very interesting. And I apologize if there are several people in the audience that have already published what they think might be much better data than this, but I just pulled this one out as an example, showing how people estimate from a surface magnetic field measurement, which we can do rather accurately with vector magnetograms, and combine that with soft X-ray technology to try and determine the nature of a twisted structure coming out from the sun. And the idea is to use the X-rays to constrain an extrapolation from the surface so you can figure out a quantity called the helicity. And it's got a magnitude and it's got a sign to it. And the idea here is you use the best techniques possible, but you can see a limitation here. Many of those CMEs come from regions where there aren't any sunspots at all. And it's very, very difficult to do these vector polarimetry this to the level you need to extrapolate things other than outside of an active region. So this is going to address part of the problem, but this, I believe, does represent a state of the art. The problem is that, oh, that's not come out very well. These are scatter plots. And the whole point of this is to show that when you do this process and you evaluate the helicity as measured in the corona from that projected from beneath with the magnetic fields, not just the helicity, actually, just alpha, which is the curl of the magnetic field. So this is related more to the current helicity than it is the actual magnetic helicity, but it's a quantity related to that. And you can see very often there is actually a almost a plot here. In an ideal world, you'd have something like this here. So if this is the state of the art, I think we can probably do a little bit better than this. And we can also fill in the gaps by looking at regions of the sun where CMEs come from, other than active regions where you can do this. And here is one example here. And this is an old one, started by, in the 1960s by a whole variety of people in France, and then over here in the 70s. And the point is to try and use observations of the corona now, so directly measure the actual magnetic field vector, if one can, in the corona. Has only become possible in a couple of cases. Only one or two demonstrated cases I know of where that's been really possible. But those have been done with very crude instruments, 50 centimeter, 40 centimeter coronagraphs, and we now have a 4 meter one coming online. So what am I showing here? Well, we're looking at, the idea is to look at these lines that lie in the corona. As you know, much of the X-ray corona is in X-rays. That's about 1,000 MeV, 1,000 electron volts. 100 electron volts is EUV wavelengths. And that's characteristic of normal kind of transitions, like in hydrogen, from n equals 1 to n equals 2, but for more highly ionized species. The energy goes as the charge on the nucleus squared of the transitions. So for instance, oxygen 7, oxygen 8, hydrogen-like oxygen has its resonance lines down in the 20 angstrom region. So looking at X-rays, you're looking at those kind of transitions. But there's another class as well, in which when you have multiple electrons in the lower level, you have a combination of the levels have more than one level associated with a configuration and a term. And unless it's a singlet S, like in, if you have, say, a boron-like ion, you have a splitting in the lower levels, and that's a 3 halves to halves transition. It's not allowed electric dipole transition, it's magnetic dipole. So intrinsically, they're rather weak. But as you go to the corona, those dipole transitions vary as something like Z to the power of 8. So you start to get a very much stronger transition in the corona than you would ordinarily have in a very low-lying atom. And so when these lines show up, they show up at about 5,000 angstrom in iron 14. And in fact, these were the lines that used by Ed Lane to demonstrate that the corona was hot. That was just such an ingenious piece of work because there was very little in the way of laboratory data. He had to do a lot of extrapolation, interpolation, and all kinds of wonderful things to write this amazing, absolute slam dunk paper on what these ions belong to. And so, anyway, over many years, they observed 1 micron lines. I'm showing you something here which I think is absolutely very fundamental to understand. Here's an observation that, with the help of Bill Livingston at the NSO, Steve Tomczyk and I, Matt Penn was involved, others, we tried to observe a coronal line from Kitt Peak National Observatory. Well, this is clearly hopeless. I mean, if you've ever been to Kitt Peak and looked at the sky, I mean, you can put your thumb up and you still get blinded by the sun because it's scattering around in a halo. And that was indeed the case on these days. But if you go to 4 microns, it doesn't matter. Factor 10 in wavelengths makes all the difference. Rayleigh scattering goes as lambda to the -4. Lambda, yes. And if most of the molecules have their energy, say, at a, equivalent to 1,000 angstrom, lambda 1 micron minus 1,000 is essentially 1 micron. It goes as lambda to the minus 4. And so on that day, we could measure something which was about 3% brighter than, quote, the continuum. That's not continuum. That's scattered light from the garbage in the sky. But by a careful differential measurement between an active region and the north poles of the sun, where there was very little emission at all, because we knew from the measurements of trace and what have you at the time, we were able to show that we measured this line of 8 times ionized silicon, right near 4 microns, with a non-systematic signal-to-noise of about 30. The systematics, you know, it doesn't make any sense to talk about signal-to-noise if you have systematic errors anyway. But this was an amazing thing. Not even a coronagraph and not even coronal skies. If you go to Haleakala, if you look on our HAO site and go to the front page, and there's a small article about a trip that Michael Knilker and I and others took. I have a photograph there showing a picture of a blue sky with a pole sticking on it. And the pole is taken, it's a girder, part of the construction of the ATST, the DKIST, with the sun behind it. If I moved like that, I was blinded. I put it there. And you look at that picture, there's very, very little sky there at all. So this would drop by a factor of at least an order of magnitude, maybe 100, this particular background brightness here. So I think you can see it's a game changer. Go to a good coronal site with a 4-meter telescope. Can it measure things like helicity? Well, I don't know yet, but I think it's worth the effort. This is an example of some calculations I did from a very simple analytic solution, very cleverly put together by these guys, in which we have a thing like Saturn. We have an electric current sheet here. These are all potential fields outside of the potential surface and outside of this current sheet. And change the magnitude of the current sheet to see if we could simply see in the Stokes profile of these kind of lines, if magnetic field were actually changing, and if we could see a difference in a thing that has a lot of magnetic energy in it, namely in this sheet, compared with one that doesn't. So here's an example of linear polarization, and there's a difference between 2 linear polarization maps differing by a factor of 2 in the strength of the electric current only. It's not just the change in the amplitude of the polarization, but the actual vectors change as well, if you look carefully. They change direction as well by 90 degrees in some places due to a special Van Vleck effect. But all this is due to the fact that all that's going on here is the magnetic field in the plane of the sky is changing. And the strength of that field pulls the field lines towards it or pushes them away, the strength of the current, according to the Biot-Savart law. So indeed we can detect that. The Stokes V profiles show interesting differences between the two things as well. This is old data, the old study published by myself and colleagues earlier this century. Notice how weak these signals are, though. This is in units of the Stokes V intensity. It's still an intensity. It happens to be in a polarization state that's called P, which is circular right minus circular left. It's about 10 to the minus 4 of the intensity. We already know how difficult it is to see the corona at all. And at the moment, it's very difficult. Nobody's actually really detected this apart from Hao Lin with a very long integration. Actually, Jack Harvey claimed to detect some of these things with photography, and they look like real detectors to me in his PhD thesis in 1965 or so. But this is a very challenging problem. Remember, helicity is b squared times the volume times length. And so you have, to measure the magnetic field, if you have an error of 10% of the magnetic field, your error in b squared is 20%, etc. So this is a challenging problem. And you need a big telescope. We've got, guess what, guys? We've got big telescopes on the horizon. Here's another example of a really twisted field. And I was hoping to demonstrate the difference between one configuration and another one. But in fact, in the AppJ letter that came out, there wasn't, I don't think, sufficient information there. This is one of Sarah Gibson's and BC Lowe's Spheromac models. This is looking along this thing. This is looking down on it. And I'm going to show you an image of the Stokes polarization as seen along the throat of that particular structure. And hit by it is actually something measured by the comp instrument, which is a 20 telescope. 20 centimeters is a bit smaller than 400 centimeters. It's 400 times less flux to start with. This is already kind of interesting. It shows that the Spherimac model is not in complete disagreement with what we see at the edge there of the sun. The Spherimac model is carrying a big amount, a very well-defined amount of helicity with it, and we should be able to get at that with these big telescopes as a result. Furthermore, when we see these things lift off, we have a cosmo which will be trying to be observed in a synoptic fashion, then we will indeed look at the lifting off of helicity into the corona, if we can measure these things. Okay. Let's take a step back for a minute. These are some of the strongest lines that I determined many years ago to try and look for in terms of diagnosing the magnetic fields in the corona. Magnetic sensitivity is linearly proportional to the wavelength. And what you see is the absolute longest wavelength line that have ever been detected is this one here, the one with the detection I showed you. But there are several others in here, and these are the ones that I could think of that would be potentially strong in the corona. The thing that's missing here is you should use all the data you've got when you observe in this kind of conditions. And pretty much every time you see a CME, or many times you see a CME, there's going to be a filament there as well, or a prominence. And there are many lines of Rydberg series of hydrogen and helium in here that I haven't included as well, which should be used for the determination of magnetic fields using a combination of Zeeman and Hanley effect. They could potentially be, in fact, the most important ones, because they're going to be so much stronger than the coronal line. Pick out along the corona some special place where the gas happens to be cool. Remember, the gas is never really dynamically significant in the sense of the plasma beta. It may well predetermine the structures that you have because gravity pulls down on the matter, the magnetic fields then support them. That's intrinsically a not force-free situation, far from plasma beta being zero condition. But nevertheless, one should and use all the information one can, and I think it's, I mean, there are many lines of hydrogen and helium in here. There could well be lines of, for instance, magnesium, which we see, magnesium-1 is a very strong line at 12 microns, photosphere of the sun, for instance. If that shows up in prominences as well, then we could really be in business here to try to look at the vector field over a volume of the sun. And, but anyway, the point of this is to show you that this is the line that's been used mostly to determine the magnetic fields. And there are lines at far longer wavelengths, and the magnetic sensitivity is very, very much stronger in these lines. There has never been a complete spectrum taken, spectral survey beyond about 2 microns of the sun's corona, ever. Okay, let's look at the infrared. So I'm going to speed it up here. It's not a open window. There are many windows that are shut to us, but it's mostly shut by the fact that we have water. And at longer wavelengths, one also gets various other things as well. But in this region, down to about 3 or 4 microns, you're mostly looking through holes in water vapor transmission lines. Well, guess what? Haleakala was picked partly because it's a very dry site. And so, in principle, there will be regions we can't observe here, but nevertheless, we will be able to get many of these lines, which I'll show you in a moment. Before proceeding, I want to point out there is a recent review by Matt Penn, 2014. Anybody interested is really recommended to look at this. There's some very nice stuff in there. He focuses on several things. Tom Eds is not here today, so, but anyway, he gets a lot of credit for the work done in this region. There are various things to do with the atmosphere, prominences, and what have you. This famous 12 micron line here. This line was discovered by the guys down in Denver, the Mercray family. And in 1980, they published a a very nice spectrum, I think, from balloon of the entire corona out to something like 25 microns or something. And then they published this paper, and they actually looked at this region, and they were so embarrassed by what they saw that they felt like they couldn't publish it. They thought there was a systematic problem with their data. And the reason they didn't like it was because it was in emission. Now, infrared spectral lines aren't supposed to be in emission from the photosphere. The temperature is decreasing with height in the photosphere. The wings of the lines are brighter because you see deeper down. The cores of the lines are dimmer because you see further up with the temperature lower. So they actually did not publish that. They published the entire spectrum and blanked out that part in the paper. And these guys are laughing here. One should never edit one's data, but I don't think they were being dishonest at all. I think they just didn't trust what they measured. Turned out the damn thing is in emission, and it's incredibly important, but it's never really been used to its full capability, because we've never had a really big telescope to take advantage of the high resolution needed to work with a line at 12 microns along. In other words, it's more profitable to work with lines nearer to 1 micron these days because we have better detectors, we have telescopes are designed to see those better, et cetera, et cetera. So it's never been fruitfully explored. Okay. So I'm going to focus on these things. Everything hinges to a large degree on the use of the infrared on the refractive index of air. And basically, it just drops monochromatically, except when you get to rather longer wavelengths where all kinds of nasty things happen, where you start getting the refractive index messed up by actual line transitions, which is not surprising. This is all kind of dielectric theory. So when you have a line, you just add in the line components of those oscillators that you have in the atoms there. Just to show you that, so let's, and I'll get into where that comes from, what that means in a minute. So the advantages, of course, are we have very good seeing, which affects mostly observations near the disk, on the disk and near the limb. The reason I don't include that in the corona is because pretty much you don't want to go anywhere near the diffraction observing the corona. It's because you don't have enough photons. So when you do that, you get so far from pretty much the seeing conditions, even on a very good site like Haleakala, that it doesn't really matter. You have very low scattering. You have increased Zeeman versus Doppler effect. This is the lambda to the power of 1 I was talking about. And that you have very low polarization crosstalk. The disadvantage are you have this stuff. It used to be a big disadvantage that the detectors were very, very expensive. You also have to cool them. And furthermore, you lose some angular resolution. I'm going to elaborate on these now and show you where this stuff comes from. Now, the bottom line of all this, I mean, this is probably too much information here. There's several very important things here. Further you go to the infrared, various things happen. You need far fewer AO, adaptive optics actuators. These are deformable mirrors. And with a 4-meter class telescope, I don't think it's clear to anybody yet if it's really going to be capable of doing the corrections needed to get use really good diffraction-limited stuff in the visible regions for a very large field of view that you might be interested in looking at. Over a very narrow one, that may be true over this isoplanetic patch. So this is very important because it means that if you go to, say, instead of 5,000 angstrom, you go to 50,000, 5 microns, you gain by over a factor of 10 in the number of actuators you might well need. It's just in the diameter, so it goes as the square of that. Okay, another one that's very interesting is that the coherence time of the seeing is much longer as well. So you can use an even slow AO system. That's very nice because these things, to do this in the visible, you need kilohertz frequencies at least to modulate these mirrors, and that's really kind of pushing the limits. Furthermore, you get a much better, essentially, to combine these two, as I summarize these things, you essentially get much higher contrast images, easier to convolve, subject to the fact that you've already got a bigger area spread function because you've got a lower diffraction, lower resolution, angular resolution. Okay, that's the AO part. And those come from the refractive index. Okay? Scattering, well, essentially, this is a measure of the brightness of the scatter of the sky, measured in the 1960s. You can find this in Penn's review, which is very nice. And this is just between, say, 5,000 and 5 microns. These slopes are very steep. So again, we get very little scattered light from the atmosphere. The roughness and cleanliness of the optical surfaces is either flat or a little bit better in the infrared. In terms of diffraction, of course, they have something like this. And DKIST is sort of an off-axis, highly polished chronographic quality telescope. We're going to be wanting to push this stuff down as far as we can so that we don't get just this added noise all the time. Okay. I don't really need that one. This is very important, I think. This is a representation of a Muller matrix, and I apologize for those not familiar. This is diagonal part. So this is saying if this is the basically telling me how much of the done solar telescope. This is measured between 400 and 1.6 microns by Socos Navarro. Essentially, you want as diagonal a thing as you can get, meaning that if I measure an incoming light multiplied by this matrix to get, I have incoming light here, multiply it by this matrix here, these rows in this matrix, to get my Stokes vector here from which I can extract magnetic information, I would want 1, 0, 0, 0, because I would measure the intensity. And I would want 0, 1, then I'd measure linear polarization, 0, 0. And you can see that these are almost, getting close to 1. The important thing is, this is wavelength on the x-axis. You see that they peak around, many of these things peak around 500 nanometers, or a bit longer, which is rather unfortunate. But they all, asymptotically, are pointing towards 0 in the far infrared. So basically, you get reduced polarization crosstalk. It's much easier to determine fractional polarizations with a higher accuracy in the far infrared than it is elsewhere. In particular, for the coronal problem, I put these things together, we see what the predicted spectrum would look like above a background at a very, very, very good day of seeing 20 millionths, I think is what I used here for the brightness at 1 micron. And here you can see the optimal line of iron 13, which is what Cosmo would use. Here's the actual atmospheric absorption. There's very little absorption there. There is some, it's not 0. And here's the solar spectrum. And this is the Stokes V. And this is what you get in a few minutes of integration with an absolutely ideal instrument. And these numbers are a few 10 to the minus 4 of this one here, of the intensity. So far, the comp instrument has been able to measure that. But that's not a research instrument. That's a prototype. Now I look at 3 microns, and you can see some of the problems we have and why we're justified, in part justification for the eclipse. So here is a line of 3.028 microns, which has never been properly detected. In 1967, Guido Munk, who was a student, I think, of Chandrasekhar, flew on an aircraft and tried to measure some specific infrared lines, and he got a sort of 2 sigma detection of this guy. So that is what it is. But what I want to point out is here is the uncertainty in our laboratory wavelength for this line. And so if this line happens to lie right here, we've got a funny-looking H2O absorber, and if that's changing with time during our observations, the polarimetry is off. You've got to have an absolutely clear sky to do that. Now, if the line, though, happens to be over here, centered here, we're in real trouble. We've got no blue wing at all. If it's over here, we might be quite well off. We're starting to get 0 gradient here. Part of the reason to go into and observe these things in the infrared from an aircraft during an eclipse, if you can, and it's not actually going to be from an aircraft for the experiment that we're running for financial reasons, is to try and determine where these lines really are relative to these background, to this Earth, because we're going to be using the HEST. Okay? So that's one reason. And it's a very important reason. So let's move straight on to the eclipse. So what are we trying to do here? Well, when I've looked at the science that's been proposed on this eclipse so far, because it's in the review process for the NSF and other agencies, I couldn't find very much. So I'm going to basically show you what we're planning on doing from NCAR, together with the Smithsonian Institution and NRL and the University of Torino. The other things I'm tending to find on the web are much more public outreach, which is fine. It's just that these are real, genuine scientific things, not public outreach, essentially. So there is the eclipse path, as calculated by good old Fred Espenak, who I've never met, but I'd like to. from NASA. So there is the center point of the eclipse. What we're going to do is a spectral survey of the corona from 2 to 12 microns. And we're going to do an aircraft-based imaging set of measurements and polarization. There's the G5. It won't go quite that fast, I hope. Anyway, this is a picture of the WIRO, the Wyoming Infrared Observatory, which sits on, funny name, to the southwest of Casper. Thank you, Jelm Mountain. Jelm. I wonder what kind of name that is. Anyway, here it is on the top of Jelm Mountain. This is not going to be, it's 90 miles off the eclipse path. But remember what I said. We observed from Kitt Peak with full sun on a not a good day, and we easily detected the second 9 line. This thing is going to be 96.3% eclipse at the maximum. That means we've got 25 times less sunlight. As a drier site. Wyoming is drier. That's why kind of like my mouth feels like now, actually. Anyway, it's a lot drier. And so we don't know whether we will use the infrastructure that's already in place here or whether we're going to go under the actual eclipse site to run this experiment. But we will have discussions, and we're going to engage the University of Wyoming with this. And the deal there is to do that experiment I just talked about, which is to measure the infrared corona and try and detect also the any material which will be there. We'll be blasting out light 100 times brighter than anything we can see in the corona. And we will not be imaging with that instrument. We will just take all the light from all the corona during totality and see what we get. Now, the aircraft, however, is going to be doing imaging spectroscopy and imaging spectropolarimetry, subject to availability of funds for these 2 instruments here. The ones that we know about, which will be running, will be an imaging spec. I'll talk about both of them. Actually, let's do that. So here's the list of lines, which I showed you before. Here are the absorbers again. Here's the transmissions. I don't know why. I can't remember why I computed that at 8 kilometers. That was for a previous airplane flight. Anyway, so we're looking to find some of these things out here. And here are the details of the ground-based spectral survey. The only reason this is not flying on the aircraft, this is an aircraft-designed instrument, is because we couldn't find the money here to do it. And at NCAR, we're not allowed to, obviously not allowed to apply to the NSF for extra money, because we already get funded by the NSF. You can't go double dipping. So it's kind of an unfortunate catch-22 for us that we couldn't get a partner that was willing to work with us on this in time to put in a real proposal and do all this stuff. Basically, Scott McIntosh is contributing this much. We're working with discussions at the University of Wyoming. That should say HAO. Paul Bryant's here, is over there. He's the science lead for this thing. And what you're seeing here is I put on the coronal lines relative to what we have, what we understand about a simulated spectrum of the Earth's atmosphere in full sun. And you can see that we pretty much stand no chance of detecting this one here. But lines like this, you know, a pretty decent whack at having a go at this stuff, providing the wavelength is not absolutely smack on a molecular band head, which we don't think any of those are. Okay, what does this look like? This is the WIRO. It's a 2-meter class telescope. It is a 2-meter telescope. It's a Cassegrain, a secondary focus here, and we probably would not benefit from using this with the FTS because you don't get any more photons. You just see a smaller part of the sun. So we would probably just go up there to use the infrastructure and prepare for the eclipse with this instrument, but we haven't. Again, this is up for discussion as yet. Jim Hannigan is the PI of this one. I call it the NCAR FTS. He calls it NCAR Airborne Interferometer because this is not airborne. At least if it's airborne, there's a real problem when it's supposed to be on the ground in Wyoming. Okay. That's still to be done. We can see the instrument, and this is sitting over in Foothills Lab N, whatever that N is, the ACOM. More details of what's going on. It's basically a simple Michelson setup interferometer. It takes 10-second scans to do an incomplete scan, and what we would plan is to do multiple scans before, after, and during the eclipse, and simply accumulate data And we will get data from, say, 1 to about 12 microns with a higher signal to noise at the short wavelength end. It's just the way the detector works. And there are actually fewer photons out in further infrared. Okay. This is the timeline for that total eclipse experiment. Now, flying at high altitude and in the infrared, observing infrared, has a lot of really good benefits here. But the problem is we have limited space on the G5. You mean image stabilization. So a large amount of effort is going into the stabilization here because they will be doing imaging spectroscopy. Notice that the bright background and the very deep absorption will essentially disappear from that aircraft. It's flying 14 kilometers up. That's more than one pressure scale height. This is not Mount Everest. This is several Mount Everests up. So this is a serious business. Here is the SAO experiment. And they will be, they already have a baseline design and starting to build this thing. And they're going to be coming out to the NCAR facility to look at incorporating this into the flight thing, into the aircraft. And we have, one important thing is that this is going to be the PhD thesis for an engineering student from SAO. She's going to be working primarily with Ed and others over at SAO. And the idea of this will be to get multiple spectral lines, a cleverly designed spectral thing, and it will scan various parts of the corona, determined the day before from images from space and what have you. And these are the target lines. And as you can see, those that are familiar with these things, this spans something like a typical coronal hole temperature up to, so this is typical solar 6.2 in the log or something. So there's a decent spread of stuff here. We really don't know anything about the brightness of these lines. And these will be seen much higher up than in the EUV. EUV lines go as NE squared. These go as NE. And in a stratified atmosphere, that's what you want. And the polarization increases. The relative polarization increases as you go further away. So it's all good. There are two other experiments which I won't focus on more than just show you this. We have not got the funding for these things as yet. We're hoping to do this. It's no longer Dan Moses. He's moved to NASA, but there's another NRL PI. And there are various interesting things to do here to do with the physics. So in summary, this is what we're going to do. We have 4 experiments. The sum of it is greater than the parts. We're going to observe multiple coronal ions, multiple wavelengths. We hope to attract at least 2 PhD students. We got one already to do the theses on this stuff. We will see. We deliver two new instruments. This is an MRI-funded one. This is our NCAR FTS. These are new packages available for the community after the eclipse. And they also will provide a stabilization system. And these guys are already planning for the next eclipse, whenever that might be. If you have an aircraft, you can go anywhere you want, pretty much. Our proposal for the G5, I was PI on that one, and their MRI proposal was successfully competed. And Scott McIntosh will fund the other one. As I said, the others are to be determined. Other eclipse efforts I know about include the AAS Eclipse Outreach website. There is the Hugh Hudson Eclipse Megamovie project, together with Scott McIntosh and others here. There is a CATE, Citizen Kate experiment by Matt Penn, who's looking to use, I believe, a set of catadioptric 12-inch class amateur telescopes all the way, 100 and 200 of them across the eclipse path, and then actually get a view of the changing white light corona is what I believe is doing, but I could be wrong, over the 2 hours or so during this time. And that will be extremely interesting as well if he gets that done scientifically. Waves, CMEs, thermal collapse of structures in the corona, whatever. I mean, it's going to be fascinating to see. So for the future, I put together the helicity to the observations, but I want you to take it as, and I think I needed to do that, and I apologize for not having a direct demonstration of how a certain amount of helicity leaving the corona would leave an imprint on the in the signals that we will be able to measure. I think in principle, there's no way, there's no sort of there's no way, there's no real block for that. And the only question then will be, how technically are we going to get the 3D magnetic field out of by observing the field of the edge? Well, this has been thought about at great length by various people. Maxim Kramar, who's been to various institutions and visited here on many occasions, has a way of doing stereoscopy. So that if you assume the sun is not rotating too much, is not changing too much while it rotates, you probe different slices of the corona. And with very high signal-to-noise ratios in these infrared lines, in principle, you can fill the volume with magnetic field, and there you've got the 3D vector field as a function of volume in the low-lying corona. We haven't even got that for the photosphere. So people that are very skeptical about the corona and their measurements, but do photospheric work, need to think before opening their mouth more, because that's a big step forward if we can do that. Of course, we haven't done it yet, but I think it will happen. ATST, I want to draw your attention to what it's claiming to do. The important part for me here are these polarization accuracies. It goes out to 28 microns, in principle. Nothing to stop it. These are the claimed sensitivities they want to shoot for. For instance, this is independent whether you observe the corona or anything. And then if you look in the chronographic mode, you want to get these kind of statistics here, and this is very feasible, and it's going to last 30 or 40 years. So if you want to do ground-based astronomy in the United States, guys, this is it. You ain't going to get any other chances unless you pay Big Bear money or somebody to do it for you, some private observatory. Goes out to 28 microns. No first light instrument beyond 5. That's the eclipse measurements need to be done. If we've got a line at 9 microns we can use, and we're still stuck down at 4, we're losing 2.5 times the sensitivity, in principle. Cosmo, again, this is only going to operate here. This is a refracting instrument, so we can't even go out beyond a couple of microns with typical glass that people are going to use. This is supposed to be a 1.5 meter refractor. You don't want to sit underneath that thing if somebody hasn't screwed it in right. Okay, so in summary, above 2 microns, coronal prominent spectra are basically not largely unexplored. The models that show that new telescopes and instruments will address questions of great importance to the solar dynamo. The goal here is to trace not only the magnetic field exiting the corona in CMEs, but to track the amount of twist and quantify that, and look at the signs of it as it's emerging out here. This then, we look at the kind of theoretical work that BC and colleagues and Axel and others starts to be a big impact for the evolution of the solar magnetic field itself on 11-year timescales. We definitely need to find out if the spectral lines are observable or not just because they're not there, but because they're behind something that we can't see through. Hopefully, the Eclipse 17 campaign aims will be successful, and I particularly want to thank Scott McIntosh. Without his support, this would not ever have got off the ground, essentially. And Wanda Grubisic was extremely helpful. And she's the director of the EOL, which is the NCAR institution that takes care of the aircraft. And Ilya Rusev has always been encouraging the NSF, and many others who I can't mention here for their support. And thank you.
I should say that I've been to HAO for 18 years. The first time I witnessed the host lost his seat in the front row. That's how packed we are today.
What?
Excellent science that you presented. It looks really very exciting for the future here. I would like to know whether you think you can actually get the full Stokes vector out of the emission in the infrared. The emission is diffuse. It comes throughout the entire corona, right?
Yep.
So you will have Faraday rotation. You will have to disentangle the entire signal as we go through the sun.
Yeah. So in the infrared, let's see, Faraday rotation works by, that's the one where you have free charges, and the propagation of electric vector rotates because of the magneto-optical effects. Yeah, the biggest problem is not to do with the theory. which we can incorporate at all levels as deep as we want, I believe. I mean, people like Roberto Bizzini can calculate almost anything in this regard. And now we don't include Faraday rotation at all, because we never detected V. It's probably a small component to what we will have in circular polarization anyway. So the point is, though, that yes, you're asking, is it worrisome that we have yet to detect really a strong Stokes V signal? And I would argue, yes, it's still a worry, but remember, the detections have been made at 1 micron. Now that is a pretty good line to use because it's sort of in a sweet spot, but the infrared lines as we go further out to 5, 7, 9 microns could well be, we could be in for a bit of a surprise as how good those might be. So I still remain hopeful, and my theoretical predictions are that they will be there. It's just a question of whether we fit between the wallpaper lines or not, in some sense.
As I will present in my colloquium in 2 weeks' time, I will actually we'll be talking about a method that where we can actually use the Faraday rotation as to our advantage.
Okay.
So it's not actually a disadvantage at all. But it does require that we are able to measure at least over a certain range of lambdas by maybe a factor of 10 or something.
Oh, yeah.
Is that do you think that is also possible?
With DKIST, in principle, you should be able to do
but
that.
now
Yes.
during the eclipse, for example. Yeah, DKIST.
Oh, during the eclipse, factor of 10 in wavelength.
Try at least.
No, I think it's probably too late. I mean, if you have a way to put a team together and build an instrument that would do that specifically, that's how I would do it. Just sit in the Eclipse path and do what you can. You're talking about continuum radiation?
Yes.
Okay.
Or covering different lines, of course. That's the other possibility.
Yeah. Okay. Well, I look forward to your talk. Yeah.
Right. Yeah.
Phil, does infrared line go through demand splitting in the presence of magnetic field? And if it's so, then will it be much bigger compared to normal lines? And in that case, will it help understand the polar reversal process better?
I missed the very first part of the question. The rest of it I got about the Zeeman effect. But
I was asking whether infrared lines go through demand splitting also
Yes,
in
that's-
the presence of
okay.
magnetic.
So what I didn't say was that the infrared lines that we see, unlike the photospheric lines are almost always dominated by the Zeeman effect, both in circular and linear polarization. The circular polarization is always easier to measure because it's first order in a first small parameter, which is the Larmor frequency divided by the Doppler width frequency. The coronal lines are form in exactly the same way, except that we have an optically thin plasma, we integrate through the optically thin plasma, but now the magnetic field is weak enough that that small parameter, the second order term, is totally negligible. So we have no Zeeman linear polarization, but we do have the Zeeman circular polarization, and that's what I showed, those simulations showed. That is a Zeeman splitting. The lines aren't split. The lines are very broad, but by taking positive and negative sides in circular polarization and doing spectroscopy, that's what the Stokes V measures, is the Zeeman splitting, essentially. Yeah. So, and that number goes up linearly with wavelength. I mean, imagine just, I'm kind of hopeful that there is this 7 to 9 micron line that's out there that's 9 times more sensitive than the comp line. I know it's not going to be as strong in terms of intensity, but when it's 9 times more sensitive, you might be in a regime in which things balance out in your favor. Michael?
So let me summarize your talk and then come to the question. I want to make sure I have understood this right. You basically made the point that any periodic process, for it to occur, it requires a beat mechanism and a loss mechanism.
Yep.
And The problem that you have then concentrated upon here is a loss mechanism, because as we now understand, it is not just to get rid of magnetic flux, it's important to get rid of the helicity.
Yep.
And you demonstrated that very nicely. Now, the problem is how to measure the helicity loss in a way that I've yet to see what is necessary in terms of quantification of the loss to then say, okay, this is how the loss mechanism works.
Yeah.
And secondly, the second problem that I see is if all these future measurements work, then at any given time you only characterize sort of one plane of a particular structure. And there along came this gentleman you quoted and said, oh, but with time, sort of, we will get the 3D structure. That, of course, is then not very different from the situation before, because, I mean, we know for a long time that somehow the sun manages to reverse the field over a solar cycle to get rid of it. And if you just be able to characterize field structures in terms of the surviving the long-term structures, you don't catch the very loss. That's the problem I have.
Okay, so I know what you're saying, but I will counter that by saying that it's well known that in order to get a flare, in order to get a CME, this is not driven immediately by, there's not enough energy coming through the shallow layer of the photosphere for it to do that. You have to integrate that energy up a long time, and it has to be stored in situ. And then finally, the last straw is put on the camel's back, and bang, the thing goes off. I think we can capture that. I hope we can capture that. I mean, ideally, what I'd want is one of these spectropolarimeters at Haleakala and another one out at 90 degrees, like the stereo missions were. So I agree, you don't catch the dynamic phase, but by that time, the argument is it's all done. The energy, it's the storage of the energy and the helicity. And if you measure that thing through a 3D slice by doing a little bit of tomography and watch that thing, and the next time it's come around, it's gone, you know for sure that something has gone containing a net helicity and bodily taken out of the sun. So I think in that sense, I can probably argue that that is a sensible measurement to do.
Okay, so you're just saying you will characterize the helicity that has been stored in the structure before you lose it.
Yeah.
But then still, I would like to see an estimate how many of such events you will need to extrapolate an overall quantification of the loss. And probably you can do that.
You know, I'm essentially an observational person, I guess, and I would say that this subject is an area in which, you know, from what I've learned from the theorists in this area that I quoted, there is an interesting problem to solve. I've tried to identify a way to address that problem, and I would say, look, you know, we just take data with the instruments we have. We built this, you know, $300 and whatever million instrument. I'd like to see some measurements of things done with it of this type. And furthermore, I'd like to suggest that we consider a second generation instrument that goes out to 28 microns. Why wouldn't we? We've got the reflection coating to get there. I think that may be a waste if we stick below 5 microns. I don't understand why we have two instruments in the infrared, one of which goes to 5 microns, the other one of which goes to 5 microns. That's a very strange situation to me. Now Jeff had a question.
More of a comment. Namely, I look forward to I look forward to when DKIST is operating to see high-resolution magnetic field strength maps of the solar photosphere. That would be an enormous innovation compared to magnetic flux maps, which we have today. And the second comment is, probably many people here in the room will like to go to the solar eclipse of 2017. I encourage you not to go there that morning because you will never get there.
Okay.
Traffic jams.
Yeah. I was thinking of going on the new MATLAB train that they're developing from between Laramie and Denver. Okay.
Let's thank Phil again. Thank you very much.